Hi, my name is Michael, and I will present to you Too Relaxed to Be Fair, our project with Perrot and Ulrike von Luxburg. In our project, we were considering the task of fair binary classification. A typical example for a consequential decision-making process would be a college that tries to decide if a student is admitted to college or not. Either the student is accepted, then this would be symbolized by a plus in this picture, or the student is rejected, symbolized by a minus. And furthermore, the students belong to one of two groups, either they belong to group blue or to group red. And finally, we are provided a fairness notion that determines if the classifier deployed by the college is discriminatory in some sense towards one of the two groups. And then the final goal in this setting is to find a classifier that is accurate while being fair to the sensitive group with respect to the fairness notion that we were given. In our example, let's now consider acceptance rate as the fairness notion. The group red has a 50% chance of being accepted to the college, while the blue group only has a chance of 31% to be accepted. That means the red group has a higher chance, and therefore this could be considered to be unfair. This is what we would call demographic parity, and we measure this with the difference in acceptance rates. So in this case, the difference would be 19% because the red group has a higher chance to be accepted. We would like to have a DDP that is 0. That would be a fair classifier since the acceptance rates are equal. If the DDP is negative, that means the blue group is disadvantaged. But how do we actually find now a fair classifier? How do we achieve fairness? Well, the fairness constraint is non-convex. That makes the optimization very hard. We can visualize this in the plot on the right. Each linear classifier corresponds to one slope and intercept. And we can plot the corresponding fairness value that this classifier achieved. So for example, the linear classifier on the left, we have seen that it advantages the red group. The corresponding slope and intercept has a red DDP value. Therefore, the cross lies in the red region. That's where the red group is advantaged. If we would change the classifier, we could end up in the blue region of this plot. That's where the blue group is advantaged. And we want to end up in the yellow region. That's where the DDP value is 0. And as I've said, the fairness constraint is non-convex. And we could decide to make optimization easier by considering a fairness relaxation, a proxy value that tries to approximate the fairness value. And then this function could look like this in the plot. And it would be easier to find a spot where the cross lies in the yellow region. And we would obtain the classifier on the left. But if we double check the fairness value, we see that even though the linear relaxation value is 0, we don't have fairness. The DDP value is still 17%. The fairness was not well approximated by the linear relaxation, and we could not reliably learn a fair classifier. Our solution to this problem is search fair, which can guarantee a fair classifier while still using the relaxation function in the method. So in conclusion, we found that convex relaxations cannot reliably learn fair classifiers, and we propose search fair that can guarantee a fair classifier while using many existing relaxations. If you want to know more, check out our paper, which we will link in the description below, and thank you for watching.